Good morning, friends. Myself, Professor Chaubey. You are in the Professor Chaubey's physics class under the heading Physics Made Simplest. Well, today I am going to talk something more about the electrical measurements. Well, we have not discussed so far an instrument known as a potentiometer. You see, as the name is potentiometer, it means something which measures potential difference, potentiometer. While potential difference can be measured by the simple voltmeter, multimeter, no problem. Voltmeters, remember, a voltmeter is a device. When we measure the potential, current will flow through the voltmeter. So whenever we measure potential EMF, we want to measure EMF of a battery or cell, we cannot measure EMF. EMF means when no current is drawn from the battery. But when a current is drawn, when you connect a voltmeter, always some current will flow through the voltmeter. Without current flow, there will be no deflection in the voltmeter. So whenever you measure any potential difference across any battery or any 2 points, current will be flowing through the voltmeter. Only then deflection will come. So when current is flowing, there is potential drop, and when potential drop is there, due to internal resistance of battery, there is some potential drop, and you never measure EMF. You measure only potential difference of the 2 terminals. The potentiometer is a device which can measure the EMF when no current flowing. I will explain you how potentiometer measures EMF, how it can measure the not the potential difference but EMF, electromagnetic force. That is the no drop of the potential. So potentiometer is a simple instrument. Earlier it was 10 wire potentiometer, a cardboard long having 10 wires. You can have some other potentiometer also called a student potentiometer. You can have single 1 wire potentiometer. But the principle is that we have a main circuit using the battery or the cell. I have say a battery or the cell. This is a battery lead accumulator, you can say. We have a key here. We have say a rheostat here which can change the current. This is a variable, the rheostat, and this and this is the main circuit, say battery rheostat or the current control rheostat here, and this is a say a straight wire here. You can have say 1 wire or many wires, 10 wires potentiometer. So potentiometer, now the principle is that the whole potential of this or EMF through the rheostat is dropped across these 2 points. You can have say these 2 points A and B are the points where the battery, this is connected here, and current is adjusted. So this battery potential, say EMF, say E volt, is dropped across the wire of potentiometer. remember this. This is the main circuit. Connect here the key, and then current will flow. And this is long wire, maybe 1 meter or 10 meter, depending upon. Now, earlier there were 10. So this is on the card, on the wooden board, and having a scale also, so you can read. So this is connected like this. And this is the main circuit. So the wire of the potential, it was dropped across the wire of potentiometer, say of length L. L is the length. Then potential gradient. The potential gradient means, say, you can write by any symbol. Potential gradient, say I write so by G, is equal to potential, say E over L. This is important thing, that E over L can be made very small by taking E small and by taking L large, means 10 wire potentiometer. And so this is the main thing, that a potential gradient is produced. A potential gradient produced of desired value. We know of the order what potential you have to measure. So what is the potential? So how much potential gradient, means potential difference per unit length of the wire, should be required, so that we can read the our potential across the whole wire. So that way potential gradient is produced, that the total potential of this wire must be more than what potential you are measuring. So that the principle that you produce a gradient of your desired value, so that you can read your whole potential difference across any 2 points on the wire. The wire length must be more than the potential of the instrument or potential of the cell you want to measure. So this is the potential gradient is produced. That is the important thing, that you have long wire, 10 wire device on the wooden board having a scale, and say you can read the length of the wire on the scale. And now what you do? You have the auxiliary circuit, same point here. You connect, say, a cell. This has got, say, a galvanometer and a variable wire. So means you have galvanometer and a variable wire. This wire can be connected anywhere. Anywhere you can move this. So this potential, remember now important thing is that this is a positive end, so this is the positive end. So positive end of this cell is also connected at the positive end here. If you reverse, you cannot measure potential. It will be opposite. So the positive must be, so this way the potential EMF of this cell here, you know the gradient, so you know if I connect here and see no galvanometer current, no current zero, means no current flowing through this or this, means this cell no current flowing, means we are measuring, we are balancing EMF of this cell on the wire. So how much EMF of this? Suppose this is the length, is say L1, then L1 into G is the potential here. This potential is L1 into G. G is the gradient. So L1 into G, it means this potential If the potential is less, a current will flow in galvanometer from this side. So this is A, B, well, I can call this a C or D. So D point you can vary on this wire. So when D is here, the potential of this wire is less than this, the current will flow in the galvanometer from C to D. If, so this is a E, this is a E1. If E1 is more than, if E1 is larger than L1G, the current in galvanometer will flow from C to D. Otherwise it will be if E1 is less than L1G, the direction will be opposite. So in this galvanometer, either current flowing through C to D or D to C in the galvanometer will be left deflection or right deflection. Where the potential of this wire, maybe I have AD wire, is equal to the E1 value, no current flowing through the galvanometer. It means the potential of these point D, A and D is balanced by the potential of it. Equal. So this potential is equal to this. There is no current flow. So that way we can measure EMF of the cell, not the potential difference, because no current flow means no drop due to internal resistance. So we measure EMF here. So this potentiometer, a 10 wire, you have say long wire, and you have this last end VS starting at A, and like current flowing this. We can connect now. Now this can be used to compare the EMF of two cells or more cells. Means we connected here another cell and we see measure what the L2, where the EMF of the other cell is balanced. So that way you can compare the E1, say E1 over E2 is L1 over L2. L2 is the length of the other cell. So we have two cells, then we can compare the EMF like this. So we can connect a key here also. So that we connect key here, this is connected here. We remove the key and then we put another cell here, the E2. Put the key here, this cell is connected, this is removed. So we can compare the EMF of two cells. If we have say two cells, Lagrange cell and say Daniell cell. We want to compare the EMF of these two. We connect here Lagrange cell, we connect here Daniell cell and do the experiment. Means measure the length where the deflection in the galvanometer is 0. On here it will be left, here it will be right. So we measure the length where deflection is 0. That means the potential is balancing here. So potential of these 2 points is equal to potential of this. So that way this device known as potentiometer, because we measure the potential across 2 points, can be used to measure EMF of the cell. Means no current is drawn from cell. Whenever you use voltmeter, always measure potential difference, not the EMF, because current will always flow through voltmeter. So this is the beauty of the potentiometer. Now this can be used for various experiments. Potentiometer also used to measure the low. By adjusting the, you see this rheostat, you can change the gradient here. So you can measure low voltage also by changing by making gradient very low. So this is used for measuring thermo-EM also. We can do experiment where we have thermocouple and thermocouple has potential as a millivolts. So that can be, potentiometer can be used to measure the. Now there are improved potentiometers in the boxes, a student potentiometer where just we have to, everything is inside the box, wire, etc., resistances, everything. Just we have to connect with the terminals, required thing, galvanometer and cell, etc. So this is very nice device to measure EMF of the cells. This gives you EMF and not the potential difference. But name is potentiometer because it measures potentials. Now either we will be doing some problem or we will be discussing, say, some more physics of problem type. So let us see what we can do. Problems, or we do the physics. So let us see. I have a book here. So from this book, what we can do. There may be various experiments of potentiometer, and so that I am not discussing, but I am discussing principle and application. What we have. Say, problem. A simple potentiometer circuit potentiometer circuit having 1 meter wire. Now 1 meter wire also has a resistance of 2 ohm. The resistance of 4-volt battery is negligible. The resistance of 4-volt battery is negligible. If the variable resistor R has got value of 2.4 ohm, if the variable that the rheostat resistance has the value 2.4 ohm, has the value of 2.4 ohm. What will be the value of wire length to give zero deflection? So, what so we have the circuits. Circuit very simple. No problem. Just I have given earlier. But part of the solution, resistance of the primary circuit, the main circuit. The resistance of the primary circuit. Primary circuit means main circuit. How much resistance they have? 2 ohm. 2 ohm resistance and 2.4 ohm variable resistance. So resistance is 2 plus 2.4 is equal to 4.4 ohms. Current in wire AB is equal to what the current? I is equal to potential is 4 volt, resistance 4.4, so 4 divided by 4.4. This is the current equal to 0.91 ampere. So this is the current flowing through the potentiometer wire. So now what is the resistance of AB wire? The simple potentiometer circuit has shown using a uniform wire AB 1 meter long, resistance of 2 ohm. So VAB, the potential B and AB is the wire, so total VAB potential VAB is how much? I flowing through this into R of the AB, and that is equal to 0.91 into 2 is 1.82 volt. Because wire has a resistance 2 ohm. And 2.4 ohm the resistance. So I can make a circuit also if you like. AB, this is the wire, 1 meter, R is equal to 2, this wire. And the main circuit here, the rheostat, battery, well, this is a battery is this is 2 ohm resistance, 4 volt battery. This is a 4 volt battery, and this resistance, variable resistance is of 2.4 ohm. So current flowing through this 2.4 and this wire of 2 ohm. So this becomes total resistance 2.4 plus 2, 4.4, and potential is 4. So we get the current 0.91. And now what is the current flowing through this is 0.91, and R is here 2 ohm. So what the potential difference at this A and B? This is the VAB. VAB is I into RAB is 1.82 volt. So here potential is 1.82 volt. The gradient, potential gradient G is equal to the potential VAB divided by N. So that is 1.82 divided by 100 meter. So 1 meter means 100 centimeter. So that gives you, or don't convert it to centimeter, remain keep meter as a unit. So the gradient is now 1.82 per meter. 1.82 volt per meter. Now E is equal to G into L, gradient into L. So 1.5. is equal to give 0. 2.4, what will be the value of the wire length to give 0 deflection? So we have here where to connect with galvanometer so that the potential of this cell, maybe say 1.5 volt cell, this balances on this. Our 1.82 is the gradient. So now E is equal to G into L. We have to find L. What is G potential? 1.5. This. So, and gradient is this 1.82 per meter. So this is equal to 1.82 into L. So L will be equal to 1.5 into 1 divided by 1.82. So this is 0.825 meter. Means somewhere here, this is 1 meter, 0.825 maybe, so this you can say balancing point here. This voltage is balanced here, then the galvanometer will have no reflection. 1.5 is the, what will be the value of wire length to give 0 deflection for a cell of 1.5 volt. So for this cell, to balance the potential 1.5, 1.82 is here. So 1.5 will be less than 1 meter. So this is 0.85 meter. Now we talk something more. So discussion type of questions, you can also discuss some questions. Say, now some discussion type of question. Discussion type questions. To understand physics, so I have discussion type questions. Where do we use Kirchhoff's laws? Where do we use Kirchhoff's laws in comparison Ohm's law? Well, when I have Ohm's law, we have an Ohm's law for resistance, potential current, and we have Kirchhoff's laws So where do we use Kirchhoff law and where we use Ohm's law? What are the answer of this? Well, you can think or simply I say that Ohm's law is a simple law used to measure the potential, resistance or current in a simple circuit. Just simple circuit where you connect a battery and one resistance is there and the current passing and you measure the voltage, you know voltage or current, you get the resistance. So Ohm's law is used for some simple circuits, while Kirchhoff's laws can be used for complicated multiple loop type circuits, many involving many components, resistance, etc. So Kirchhoff's laws are used to get the electrical currents, potential differences in the complicated and multiple circuits. And Ohm's law is simple circuits involving only one or two resistances in series or in parallel. But Kirchhoff's law, current law, voltage law, both can be applied to mesh type circuits involving many components. We have say upon which principle the Kirchhoff current law is based. Well, what is the basis of Kirchhoff current law? Kirchhoff current law is that summation of current, summation of I is 0. Means current reaching at any junction and leaving both are equal, or total sum is 0. Algebraical sum of the currents at any junction point is 0. Means the principle is that there is no accumulation of charge. Charge is not collected at any junction. Charge is not stored at any junction. Charge collection is 0. So the total current, you have one junction, many branches leaving, say here, some current reaching, some current reaching, some current leaving. We know the summation of I is equal to 0. Means currents I1, I2, I3, I4, total current is 0. Means total current is reaching and current leaving, total sum is 0. Means here there is no accumulation of charge. Charge is not stored. Charge cannot be stored at any junction. Charge is stored at the capacitor. So the principle of this is that charge is not stored. Charge is not accumulated at any point. Similarly, on what principle? Kirchhoff voltage law is based. So what is the principle of voltage law? Well, voltage law, you see, voltage EMF of the cell, we have IR dropped at the various components, resistances. So that is equal. Or total sum of algebraical sum of potentials also 0. So this is based on, say, conservation of energy. Whatever energy means or the EMF of the cell is dropped across the resistances, so IR drops. That is the EMF applied to various components or resistances equal to the voltage drop. So the energy conserved, whatever energy is applied, that energy goes to the various component of the circuit. So it is based on the principle of voltage law is based on the principle that conservation of energy. Potential applied is equal, both. So this is conjunct. And what else we can discuss something more. Well, what is the advantage of measuring potential of a cell using potentiometer? Well, the answer of this I have already explained by talking about potentiometer, that when we measure potential of any cell using the wire of the potentiometer, means using gradient principle, then no current flows through galvanometer, means current is not drawn from the cell for which we are measuring potential. So that gives us EMF. EMF is the potential difference across the terminals when current is not coming out, current is not drawn from the cell. And if any current drawn from the cell, then it becomes, due to the internal resistance, there is some drop of the EMF, and we measure potential difference. So voltmeters, etc. give you potential differences, while potentiometer gives you EMF. So this is the advantage, that reading measured by potentiometer is slightly larger than the reading measured by voltmeter. It gives more accuracy. What else? Okay. Why is Wheatstone bridge not good for measuring low resistance? Why Wheatstone bridge is not good for measuring low resistance? What problem? It can be used for the measurement of higher resistance. Because low resistance means the variation of current very small. Low resistance, a small fluctuation, you cannot read. That will not give you potential difference, and the galvanometer current will not change, because low resistances, Wheatstone bridge will not be sensitive. Sensitivity will be very small, because current change, current fluctuation will be very small. So medium resistance can be measured, not very low, not very high. Very high also current becomes small, so that change in current will not give any importance to change in the galvanometer current. So that galvanometer current fluctuation, well, cannot be detected if either the resistance we measure by Wheatstone is very low, or it is high also, low or also very high. So Wheatstone bridge principle is neither sensitive for very low resistances nor used for very high resistances, because the current change in the galvanometer is not appreciable, and we cannot read the galvanometer needle. So its current should be at least which can be detected by galvanometer. So resistances should be not very low, not very high. It should be medium high. So I think we can have such type many questions. There can be so some more problems or more questions I will discuss maybe when we meet again next time. So I can stop today here. Thank you very much, gentlemen.